Good morning, everyone. So today we will continue in mechanics with chapter 7 and 8, where we are going to discuss the energy in general and the energy transfer. So in these chapters, we're going to introduce a new approach, an alternative approach to Newton's laws of motion, because there exist some problems in mechanics, which theoretically they could be solved using Newton's laws of motion, but in practice they are very difficult to solve them using Newton's laws of motion. And that's why we need an alternative approach, easier than Newton's laws of motion and more effective when dealing with this kind of problems, which is the energy approach. So in this case, we are going to deal with the energy, which is, we can think of it actually as a quantity that can be converted from one form to another, but actually it cannot be created or destroyed. And that's why here we are going to discuss a new model or to use a new model to describe our object, let's say. And from here we are going to say that instead of having the particle model as our model for the previous chapters in mechanics and in dynamics, in kinematics and dynamics, where we were supposed to actually modelize all the objects we are studying as particles, in this chapter we are going to modelize our object as a system. So in other words, we're going to define the universe into two parts. It's like there is an imaginary surface that divide the universe into the system and the environment. The system is what we are interested in, what we want to study, and the environment is everything surrounding our system. So obviously, there will be an energy transfer, an exchange of energy between the system and the environment. And this is what we call the physical process. So every physical process in the universe, it involves energy and energy transfer, for the simple reason that this physical process is an exchange, is an interaction between the system and the environment. So how to describe and how to model this interaction through energy transfer. There is also one advantage of the energy approach, is that it allows us to understand some phenomena which cannot be described using Newton's laws of motion, like, for example, thermal and electrical phenomena, for the simple reason that the energy has different forms. It could be kinetic, potential, electrical, thermal, etc. So this helps describing some phenomena, like when the system it has electrical interaction with the environment, or thermal interaction with the environment, or thermal energy exchange with the environment. So this is it for this part. Now, how we are going to think in this new concept, in this new approach and the system model in the following way. When we are going to deal with anything, any object, or any objects, collections of objects that we are going to study, we will actually select this portion of the universe that we are interested in as our system. And we should never forget that the system, it can be influenced by the environment surrounding it through a number of mechanisms, and among which is the work. So the work, it's an important concept that we are going to discuss immediately after the introduction. And the easiest way to think about the work is thinking about it as an energy transfer. And this energy transfer, it happens between the system and the environment. So how it happens, actually you can think as if we have an imaginary surface that separates the system from the environment, and this transfer is done across the system boundary. And whenever we have an energy transfer, therefore you have definitely a change in the energy which is stored in the system. In general, a valid system, it may be a single particle or a single object. It could be a collection of particles or a collection of objects. It could be also defined as a region of space. And finally, a valid system, it may vary in size and shape. So it's not definitely something which is fixed in size and shape. So this is it about the introduction. Let's now move on to discuss the concepts, mathematical concepts in this chapter. And let's start first by discussing the work. So we've seen in chapter 5, when we discussed Newton's laws of motion, and in particular Newton's second law, that an object, if it doesn't experience a net external force, it will not change its state of motion. So in other words, if it has if it's at rest, it will remain at rest. And if it has, or if it is moving with a constant velocity, it will continue moving with a constant velocity, unless it experiences a net external force. That was the statement of the first, Newton's first law. So we discussed the force and how the force is related to the acceleration through Newton's second law. However, we don't know how effective the force is in moving an object. So in other words, let's consider as an example an eraser being pushed along a chalkboard tray. So نقول في عندكم لوح وعلى هذا اللوح في عندكم محاية. والمحاية موجودة على الرف تحت. So actually I will discuss with you a few cases, 3 cases with this eraser. Suppose that you are applying a force on this eraser, okay? In the first case, let's say that we are applying a horizontal force F. So if you apply a horizontal force F on the eraser will move, and actually it will move to the right. There is nothing surprising in it. Now, if you apply a force F, not on a horizontal way, but if you apply the force F, and this force F is making an angle theta with the horizontal in this case, so not like before, if you apply F with an angle theta with the horizontal axis, then in this case you would be able to move this eraser, but not at the same speed as previously. So you are more efficient in moving the eraser when applying the force F horizontally than when F is making an angle theta with the horizontal. And finally, let's consider the case when you apply a force F vertically on the eraser. So if the force F is applied in this way vertically on the eraser, you won't be able to move the eraser. So despite the fact that you are applying a force, and this force in both 3 cases is the same, let's say it's equal to whatever, 10, 20 Newton, but actually the motion of the object, because of the presence under the action of this same force F, is not the same. And so that's why we define the work. The work, we can understand it as the measure of how effective is a force doing in moving an object. Is it effective or it's not effective? How much is it effective? So that's why we are going to consider basically 2 cases now for defining the work. We are going to consider first the work done by a constant force, and we're going to define the work done by a variable force. Let's see what do we mean by that. So let's consider the case of a block. If you have a block sitting on a given surface, frictionless for the moment, and we are applying a force F at a given arbitrary angle. So let's say that you have some arbitrary angle with respect to the horizontal, and let's call this angle theta. Okay. So let's say this is the angle theta. So how would you define the work in this way? Okay. So first of all, the force F is making a displacement basically, which is delta R. So because, okay, under the action of the force F, you can say that the block is moving, and therefore it's making a given displacement, which is defined as delta R here in this example, and we take it along a straight line. So just for simplicity, we take the object to be moving along this, let's say, x-axis. And so this delta R is nothing else than delta x, basically. How would you define the work in this case? We define the work as the scalar product between the force F and the displacement delta R. And by definition, the scalar product is given by the magnitude of the first vector multiplied by the magnitude of the second vector multiplied by cosine of the angle between the two vector force and displacement. So W is equal to F dot delta R. It's equal to F times delta R times cosine theta, where theta is the angle between the force and the displacement vectors, as you can see in here. So let's discuss what could be this W. So first of all, W could be equal to 0. When is it equal to 0? It's equal to 0 when delta R is equal to 0, which means that there is no displacement produced because of the presence of the force F. And also in the case where cosine theta is equal to 0, which means that theta is equal to 90 degrees. What does it mean that? It means that the force F is perpendicular to delta R. Let's take an example about that. So let's suppose that we have this block and it's sitting along this horizontal surface, and it's making this displacement delta R along this horizontal surface. Okay, so what are the forces acting on this object? So we have obviously the weight given by Fg. We have the normal N exerted by the surface on the block, and we have the force F, which we apply on the block. Now, I've just divided the force F into two components. Here is the x-axis and here is the y-axis. And so the projection of F along the x-axis is Fx, and the projection of F along the y-axis is Fy. Now, in this case, let's see the work done by each of these forces on the block. So first of all, the work done by N is equal to 0 for the simple reason that N is perpendicular to delta R. So if you just want to apply this expression over there, you will end up with theta being the angle between N and delta R is 90 degrees. So this is the vector N, and this is the vector delta R. And this is the vector delta R. And actually, as you can see, obviously, there is a 90 degree between both vectors, so cosine theta is equal to 0. And so the work is as well equal to 0. So whenever you have a force that is perpendicular to the displacement, this force produces 0 work, or the component of the force produces 0 work. Okay, so we will discuss this. Now let's look at the gravitational force. The gravitational force is as well perpendicular to the displacement. mg is vertical and the displacement is horizontal. So also the work done by the gravitational force is equal to 0. Now let's have a look at the components of the force F. Wfx, so the work done by the x component of this force, is equal to Fx dot delta R. Fx and delta R, they are in the same direction. They have both the same direction. So that's equal to F times delta R times cosine theta. And theta is equal to 0. So that gives back F. Oh, pardon, sorry. So it's F cosine theta times delta R, where F cosine theta is the Fx itself. So here we have two things. So we have Fx, it's given by F cosine theta, theta being this angle, multiplied by delta R, multiplied by cosine of the angle between Fx and delta R. And the angle between Fx and delta R is simply 0 because Fx is in this direction. So this is Fx. And delta R is also in the same direction. It is given by this vector, delta R. So at the end, we end up with Wfx is equal to F cosine theta multiplied by delta R. And in what concerns Fy, it's Fy dot delta R. But since Fy is perpendicular to displacement, so Fy is vertical, delta R is horizontal, then this work is given by 0. So whenever the force is perpendicular to the displacement, you end up with a 0 work. And also if you have a force which is making an angle theta with respect to the displacement, then only the component of the force which is parallel to the displacement produces a work that is different than 0. The other component which is perpendicular to the displacement does not produce any work, like in this case for Fx and Fy. Now let's move on. Also, this W could be positive or negative. The fact that W is a scalar product between two vectors and it includes a cosine theta, then as you know, cosine theta, it may vary between -1 and +1. So cosine theta could be positive or negative. If cosine theta is positive, that means that W is positive. So when is W positive? W is positive when the projection of F onto delta R is in the same direction as delta R. So in this case, you have two vectors in the same direction, like in here. When W is negative when the projection of F onto delta R is in opposite direction relative to delta R. So let's suppose that delta R is in this direction. The point is that in this case, the projection of F onto the displacement direction would be in the other direction. So F projected along this line would be negative. Okay. So this is it about the work done by a constant force. A few more comments about that. So first of all, the unit of the work is given by the unit of F multiplied by unit of delta R. So it's kilogram meter per second squared multiplied by meter. So it's given by kilogram meter squared per second squared, which we define as joule. In the energy approach, actually, when we say W is positive or negative, that is clear from the mathematical expression. So here, F dot delta R multiplied by cosine theta, it's clear that cosine theta, it could be positive or negative, and therefore W could be positive or negative. But what does it physically mean? يعني in physics, لما نحكي عن negative work, what does it mean to have a negative work? If you still remember, at the very beginning, I told you that the work, it could be understood as an energy transfer. وهي عبارة عن exchange of energy ما بين two objects, let's say. So in this concept, the work is an energy transfer. In our case, to be more rigorous, it's an energy transfer between the system, which we define, and the environment that is surrounding the system. So if W is the work done on the system, and if W is positive, that means that some energy is transferred to the system. So the system in this case is gaining energy. And if W is negative, that means that energy is transferred from the system. So the system is losing energy. It's giving energy to the environment. While in the first case, W positive, the system is gaining energy from its environment. And be careful, the work, it's done on the system in this case. So if the work is done on the system and positive, then the energy is transferred to the system. And if the work is done on the system and W is negative, then the energy is transferred from the system. So this is it for the work done on a constant, by a constant force. Now, what happens is if we have a varying force. So what do we mean by varying force? Let's consider again the case of a block that is moving on a given surface under the action of a given force F. But in this case, F is not constant. So, and we have, so this F could be Fx and Fy. It could be divided into two components, Fx and Fy. Let's actually have a look at Fx. Since Fx is the component of interest, because this is the component that produces a non-zero work. لأنه هي منا perpendicular على displacement. So suppose that Fx is varying with the position of the object. يعني Fx, it depends upon x بهالشكل هيدي. So this is the curve that shows Fx as a function of x. And the object is moving between two positions, the initial position x initial and the final position x final. So if it is the case, then how can we define the work in this way? Okay, what we are going to do is the following. So we are going to first of all, to divide the full displacement between x initial and x final into individual displacements, small displacements. يعني بنقسمه كله ل displacement صغار. هالdisplacements هن عمليا delta x. And so it's like saying that this total displacement delta x is sum over I of delta xi, right? Sum over I of delta xi. So if we just have a look at a given interval delta xi, what do we have in this delta xi? In this delta xi, if you just have a look up there, for example, let's take this one. here the value of F could be taken as the average value in this interval. So let's call it Fx. So we can, in this small interval, we have Fx acting in this interval, and so we can also define the work Wi as equal to, let's call it Fxi, and it's given by Fxi delta xi, right? So let's define the work in this. So this is delta W. Let's call it delta Wi. And so if you want to define the total work, then in this case, the total work is given by the sum over I of delta Wi. So it's given by the summation over x going from x initial to x final of Fx multiplied by delta x, right? So this is nothing else than Fx multiplied by delta x going from x initial to x final. هي عمليا Fx مضروبة بالدلتا x لكل انترفال من هالانترفالز اللي عم نمرق عليهم. هلا الفكرة هون انه لما يكون في عنا varying force we should actually define a very small interval. يعني لازم قد ما فينا نصغر هيدي السايز تبع الانترفال بشكل انه نوصل لمحل تكون كتير صغير، وبالتالي كل انترفال it describes one point in this curve. فهذا الشيء بيعني نحن عم نروح من هيدي السميشن لما نصغر كتير الانترفال بنصير بدل ما نحكي عن دي دلتا اكس بنصير نحكي عن دي اكس، يعني عم نحكي عن انفينيتيزيمال انترفال، وبدل ما نحكي عن هيدي السميشن بتتحول لانترفال، فبالتالي بنصير بدل ما نحكي عن W equals the sum of fx delta x over all the intervals بنصير بنحكي عن W equals the integral of fx multiplied by dx, and the integral goes from x initial to x final. So that's why actually the work defined for a varying force, okay, between x initial and x final, it's given by the integral between x initial and x final of fx multiplied by dx, where fx is the value, fx as a function of x, and dx is the infinitesimal displacement x. Now, if you have more than one force that is acting on this object, يعني بيكون في عندكم fx, gx, yx, etc. So you have different forces acting on this object, not only one, that are producing a displacement. Then the work in this case, the work done by net force in the direction of the displacement, لما يكون في عندنا بس fx رح نعوضها ب summation over fx، يعني رح تكون sum fx, where sum fx is the net, is the summation of all the components of all the forces acting on the object. Okay, يعني مثلا مثل الاكزامبل اللي قبل كان في عندنا different forces اللي هن mg, so you put mg x, so it's the component of mg along the x-axis plus the component of the normal along the x-axis plus the component of f along the x-axis plus etc. if you have different other forces. Okay, so in this case W would be the integral from x initial to x final of sum fx dx, where sum of x is the net force acting, and this integral is nothing else than the area of the graph under the curve. So if you just consider here this integral for one force, for example, like in this case, this integral هي عمليا الarea of this whole surface، هي الarea لكل surface under the graph. لأن أنتم عمليا هذا الشيء اللي عم تجمعوه لما تعملوا الانتجريشن. Okay. So what you need to know now from this section is that W is equal to the integral of fx dx, and in general, when you have different forces acting, the W is equal to integral sum of x dx between x initial and x final, where x initial is the initial position and x final is the final position. And so x final minus x initial is the total displacement. Okay. So be careful about this, the use of the definition of the work when you have a constant and when you have a varying force. You should not confuse both of them. Now, the total work. Suppose that we have different forces acting on a given object. The total work is evaluated in two possible ways. So let's say you have this kind of object. This block is moving on a horizontal surface where you have a friction in addition to the other forces that are previously shown. So عندنا الweight, عندنا normal, عندنا a given force F applied, and you have a friction between the block and the surface. So في طريقتين لحتى نقدر نجيب the total work done on this block. So either W is the sum of the work of individual forces acting on the object. يعني we write down W equal to WF plus WN plus WG plus WF, where F and G, so G is to say MG and F are all the forces acting on the object. So بتجيبوا كل واحدة وبعدين بتحطوها بقيمتها. أو في طريقة تانية هي نقول إنه W is the work of the resultant force. So in other words, to say that W is F net dot delta R, and so it is in this case F plus mg plus n, all of it this resultant vector dot delta R. Of course, assuming that all forces are constant, we use this expression. Okay. So this is it for the total work. Now let's take an example about the work done by a spring force. This is an example on the variable force. When you have, نحن هون أخذنا the work done by a varying force. Let's take as an example work done by a varying force to be the work done by a spring. So if you have a spring and then في عندكم واحدة من الاثنين، يا إما بتشدوها برا يا إما بتعملوا compression. Let's suppose that in this case we have the block, and this block is connected to the spring. Okay, and this block is pushed to the right. Now the spring, it exerts a force on the block، وعلى طول هيدي الفورس بتحاول انها ترجع السبرينج لمحله الاصلي. يعني اذا كنا if you suppose that this was the equilibrium position x0 equal to 0, and then we push the block to the right by x, then the force exerted by the spring on the block will push the block back to its original position اللي هي it corresponds to the equilibrium position of the spring. Okay, this spring force is given by F equals to minus kx, where x is the position of the block relative to the equilibrium position, so relative to x0 equals to 0. يعني قد ايه عم ينشد لبرا او قد ايه عم ينعمل له compression. K is called the spring constant, and this force law for springs is known as Hooke's law. So whenever you have a spring, you know that the force of the spring is given by minus kx. And finally, the minus sign, it indicates that the force exerted by the spring is always directed opposite to the displacement from equilibrium. يعني عمليا هون magnitude of F كmagnitude of the force, it's given by K multiplied by X. And this minus sign هي تقلنا عن الدايركشن تبع الفورس. يعني بمعنى انه اذا كان displacement to the right فهي الدايركشن على طول للفورس بتكون بعكسها to the left. واذا كان displacement اذا كان البلوك was pushed leftward, the force بتكون rightward. So this is what it tells us the negative sign. فهي عموما بتكون بالمبدأ لازم يكون في vectors، بس بكل الريفرنسز او بمعظم الريفرنسز بيعملوا definition للspring force بهالشكل هيدا. So I stick to the book, I stick to the reference, and this is the way I wrote it down. But keep in mind that this minus sign is to tell you about the direction of F. يعني هيدي الexpression هي the projection of the force F spring onto the x-axis. Okay. Now, what is the work done by the spring force on the block as the block moves from x initial to x final? So let's suppose that the block was a given x initial here. هلا هون اخذناها صفر بس ممكن ما تكون صفر, and then it arrives to this position where it is x final, for example. Okay, so if it's moving between this x initial and x final, then W it's equal to the integral of fx dx. احنا شفنا قبل شوي فوق لما عرفنا work of a varying force as the integral of fx dx. So fx is given by minus kx dx. ما تنسوا انه هون احنا بنحط البروجكشن تبع الفورس. So it's minus kx dx. So it's minus k بتطلع لبرا لانه هي عباره عن constant. The integral of x dx هي x squared divided by 2. So we end up with minus half kx squared to be evaluated between x initial and x final. So it's equal to minus half kx final squared minus half kx initial squared. So we end up with plus half kx initial squared. And so the total work done by the spring on the block is given by half kx initial squared minus half kx final squared. So for example, the case spring force is an example of a varying force that depends on the block's position. This is it. Okay, let's move on now to a very important theorem, and also to a section where we are going to describe the first type of energy, which is the kinetic energy. So let's consider a block M that is moving through a displacement under the action of a net force F net. So you have here, this is the block. لما نقول F net يعني مش يعني بس هيدا الفورس الوحيد اللي عم تعمل اكشن عليه، لا، يعني مجموع الفورس اللي عم يعملوا اكشن عليهم يختصروا بهيدا الاف نت. Okay, so let's suppose that the F net is the net force acting on this block, which has this direction, and this block, it undergoes a displacement delta x between x initial and x final. So in this case, let's write down W. So the total work, the net work, would be equal to the integral of F net dx between x initial and x final. So here we have taken the integral because actually we are taking the general case. So F net could be constant, but also it could be variable. So that's why we have taken the integral and F net times dx. Now, how much is F net? So of course here we are discussing the general case. The general case أكيد ما عندنا formula لل F net. However, we know from Newton's second law, you remember, Newton's second law, it tells us that the sum of external forces acting on a given object is proportional to the acceleration through m. So it's equal to m times a. So هون we replace F net by m times a multiplied by dx. What is a? A by definition is given by the derivative of the velocity with respect to time, so it's dv dt dot dx. Now, if you just have a look at this term in here, dx over dt, it defines v. It's nothing else than the speed. So we end up with the integral of m, which is constant, multiplied by, this becomes v dv. So we end up with the integral on the variable v, which is the velocity, and we have v in the expression mv because of this term. And of course, now it becomes the integral, it becomes between v initial and v final. So the integral between v initial and v final of mv dv, now m goes out because this is a constant out of the integral. Integral of v dv هي مثل integral of x dx, هي x squared over 2, يعني هون هي v squared over 2. So we end up with half v squared evaluated between v initial and v final. So it's equal to half m v final squared minus half m v initial squared. So at the end, we end up with this expression of w. W is equal to half m v final squared minus half m v initial squared. Now, since we know that W is a energy transfer, okay, وهون مثل ما احنا شايفين بهالاكسبريشن طلعت معنا انه هي difference ما بين شغلتين. هي عمليا difference between the quantity half mv squared evaluated at t final and the same quantity half mv squared evaluated at some t initial, sometime t initial. So بما انه ال W هي energy transfer وما انه هون في عنا quantity مكررة مرتين, so actually we can identify this quantity half mv squared as an energy, and this energy is associated with the motion of the object. So that's why we call it kinetic energy, and this kinetic energy is described, or it's symbolized by K, with K equals half mv squared is the kinetic energy of a particle of mass m and moving with the speed or with the velocity v. Okay, هي أول نقطة إنه عرفنا the first type of energy that a system can possess اللي هي kinetic energy, and the kinetic energy هي عبارة عن half mv squared. هي أول نتيجة من هذه الإيكويشن. النتيجة الثانية إنه the work done by the net force exerted on a given system when the only change is the system speed it is equal to the change of the kinetic energy of the system. يعني لما يكون في عندنا net force acting on a system والنتيجة الوحيدة إنه سرعته عم تتغير، فإذا نستنتج إنه W هو الفرق بين kinetic energy ما بين الinitial والفاينل state. So W, it could be written as W net is equal to K final minus K initial. It is equal to delta K. And this is known as the work kinetic energy theorem. So this we should know and we should memorize, of course. Now, how can we interpret this theorem? Actually, it's very easy. W is equal to delta K. So delta K, it could be positive and it could be negative, right? If W is positive, if W net here is positive, that means that delta K is positive, which means that K final is greater than K initial. That means there is an increase in the kinetic energy, يعني V increases, which means that there is an energy which is transferred to the system. System ربح energy والنتيجة إنه سرعته زادت مع الوقت. The other case is when W is negative. When W net is negative, that means that we have seen previously that the energy is transferred from the system, which means that the system has lost energy. معناتها إنه delta K negative, so K final is smaller than K initial, which is very logic because V decreases in this case. So لما يكون W is positive, that means the system gain energy سرعته بتزيد. لما W is negative, حكما سرعته بقى تنقص لأنه معناتها إنه هو خسر energy. So this work kinetic energy theorem is very important later on in our applications. Now, finally, we are going to deal with the power. So this is the last topic in this chapter number 7. What we are going to discuss in this case about the power. احنا شفنا قبل انه الwork is very important concept because it actually tells us how effective is a force in moving a given object when it is applied. يعني مش مثل ما كنا نعمل قبل انه الاف هي equal to ma. هون كنا عم نشوف اي component اذا بدكم من الاف هي اللي فعلا عم تعمل او هي اللي عم تسبب الموشن او عم تكون influencing the motion واي component ما عم تتدخل ابدا بالحركه. However, this concept of the work, it does not include the time, does not refer to the passage of time. يعني ما عم نعرف نحن هالwork بأي وقت عم بيصير. إذا كان عم بيصير بوقت كتير كبير أو عم بيصير بوقت كتير صغير. So if you want to know how quickly the work by a given force is done, we need to define a new variable, and this variable we call it the power. So the power is defined as the rate at which the work is done. يعني عمليا the work divided by time. So this is the general, let's say, definition of the power. Now we can define two particular variables. So مثل ما شفنا قبل, we can define an average power and an instantaneous power. مثل ما كنا نحكي قبل عن average velocity and average acceleration or instantaneous velocity and instantaneous acceleration. كمان بالpower بنقدر نحكي عن two variables, the average والinstantaneous. The average, obviously, if you are looking at a given system and you're looking how much work is done by the force F net during a given time interval, specified time interval, then we can define the average as W divided by delta T. While in the instantaneous power, this is nothing else than the derivative of W with respect to time. So هون بهالحالة نحكي عن instantaneous rate. ما بقى عم نحكي عن a given fixed time interval between T initial and T final. And finally, one more thing to say is that, so here there are two things basically, or 2 points. The first point is that the unit of the power is given by watt. How can we determine it? So the unit of the power is given by the unit of the work divided by the unit of the time. So it is given by joule by second. And joule by second is defined as watt. So 1 watt is 1 joule per second. That's number one. Number two, the power P, it can be expressed in terms of the force and the velocity. How does it come? Okay, let's have a look at this expression. So the instantaneous power we have seen, it's given by dW by dt. So it's derivative of W with respect to time. Now, how much is this dW? We have seen actually that W in general, it's given by the force scalar product delta R, right? So if you are looking at dW at the infinitesimal work, then we should make the scalar product between the force exerted and the infinitesimal displacement dr. But this expression, we end up with this expression, could be divided into f on the first factor on one side and dot dr by dt. And don't forget that dr by dt is nothing else than the velocity v. So we end up with the power equals the scalar product between the vector force and the vector velocity v. And from here, we deduce that the power, it could be expressed in terms of the velocity and the force through this simple expression, P is equal to F dot V. And so what you need to know from this section are these three expressions. So P average, instantaneous power, and this expression, general expression for the power given by the scalar product between the force and the velocity. So this is it for the chapter 7. I just want to make a few comments, is that what you need to know from this chapter are the following. So of course, in the introduction, you can read it, etc. You need to understand the concept of work as an energy transfer between the system and the environment on one side. And on the other side, you need to understand as how effective a force is in moving the object. And always just think about this example and you will immediately remember what is the work. Then in the case of a work done by a constant force, you can immediately apply the expression W equals F multiplied by the displacement multiplied by cosine theta, where theta is the angle between the vector force F and the vector displacement. Don't forget that W is, since it's a scalar product, then it could be positive, negative, or zero. It is zero when the force and the displacement vectors are perpendicular. So whenever you have a force acting on a given object and the object is making a horizontal displacement, then if the force is vertical, so whenever the force is perpendicular to the displacement, its work is simply zero. And you can interpret the positive and the negative values of the work as an energy transfer to the system or from the system. So either the system is gaining energy or the system is losing energy. And the unit of W is given by the joule. So this is it about the work done by a constant force. Now, what about the work done by a varying force? What you need to know in this case is that the W is the integral of F times dx, where the integral goes from the initial to the final position. Fx is the component of the force along the displacement, and dx is the infinitesimal displacement. So this is what you need to know from this section. And also you need to know that W is equal to the integral of sum of Fx dx, to say that the net force acting along the direction of the displacement is the one that we should consider when we consider the total work. So this example is very important here because we have defined the spring force. You should know that the spring force is equal to minus kx, where k is the spring constant, x is the position of the spring relative to its equilibrium position, and the end of the spring relative to the equilibrium position. And you should know that the minus sign, it indicates that the force exerted by the spring is always directed opposite to the displacement from equilibrium. And finally, that this is known as Wookie's law. Also, you can also memorize this expression. That is the work done by the spring force. It's given by half k x initial squared minus half k x final squared, where k is the spring constant, x initial and x final are the position of the block, in this case, attached to the spring between initial and final time. Finally, the most important theorem also to memorize is the work kinetic energy theorem. So here we have derived this theorem, and we have seen that W at the end could be written as a difference between the kinetic energy and the final and the initial state. But you are not responsible about this derivation. You just need to understand it to understand how we get the kinetic energy kinetic energy theorem. But you all what you need to know from this section is that the kinetic energy, it has the following form. It's half mv squared, where m is the mass of the particle and v it's a speed. And the work kinetic energy theorem is given by W net equals to delta K, that is K final minus K initial. And so, of course, W could be positive or negative. Through the work kinetic energy theorem, we can interpret, or we can explain this in terms of the speed of the particle as increasing or decreasing. And finally, the power. You need to know the average power, the instantaneous power, and the and this expression, general expression for the power, where it is expressed in terms of the force and the velocity. So this is it for the chapter 7. We will go also through chapter 8 in a separate lecture, and later on we are going to solve the problems from both chapters 7 and 8. So this is all for this lecture.